So in looking at the unimolecular elimination, we saw that the DE, or electrofuge dissociation step, can follow the DN step, and that leads to the formation of a double bond. And again, we'll talk about that in more detail when we talk about the DE step in more detail. But for now, I'd like to move on to another example that involves the DN step as sort of a foundational first step for the reaction. And that's this idea of carbocation rearrangements. And so carbocation rearrangements, similar to the DN step, can precede a number of other elementary steps, and they tend to complicate the situation. So 1,2-Rs, as they're called, can come into play, for instance, in unimolecular eliminations. And you'll see an example here in a second. And they can come into play in SN1 reactions and a variety of other reactions taking place under acidic conditions. So what you're looking at here on this slide is sort of an interesting reaction in which it was noted that the predominant product was this compound here. What's interesting about this compound is that it doesn't have the same connectivity that we would expect from a simple elimination of this bromine. If we were to expect a simple elimination out of this, we would see that there are no protons to remove on this carbon. As a result, we would expect a double bond to form here at the terminal position. But we don't observe that. We actually observe a double bond forming here. And the question is, how in the world is this compound able to form a double bond at that position? Where does it get those electrons from? And how does this proceed mechanistically? So to answer this question, a great way to get a start on answering it is to think about its mechanism. And one postulated mechanism that's been generally accepted is drawn for you here. So you can see up here in the upper right we have the typical DN step where the bromine leaves as a leaving group. That leaves behind a cation here. Now this is a secondary cation. It's kind of in the middle in stability in terms of primary and tertiary. But if it could somehow become tertiary, it would then achieve a state where it's fairly stable. And luckily, because there are 3 very juicy methyl groups right next to that positive charge, it's very possible that one of those methyl groups could simply jump over, as I've shown here. And in what's called a 1,2-R step, a 1,2 rearrangement, because the carbon moves 1 atom over, we end up generating an intermediate now where the positive charge is located on a tertiary carbon. And so we've stabilized that intermediate, and this reaction is in fact overall downhill. So if I were to draw a reaction coordinate diagram for it, what I would see is that going from reactants to products, I would actually generate a more stable compound. Now, how does it actually form that double bond? Well, it forms the double bond through elimination of the proton that's actually located at that top carbon there. So it wasn't drawn in the starting material, but it is there. And by a DE step of that proton, we then get to the observed product. So these 1,2-R steps can often complicate mechanisms under acidic conditions, and you should keep this in mind when you're thinking about how a product may come about under acidic conditions. Now the 1,2-R step also can occur for simple protons. So for instance, if one of these methyl groups had been a proton, or just a hydrogen rather than a CH3, that also could have migrated to give us a tertiary cation versus a secondary. The key is that stabilization of the intermediate, going from a secondary to a tertiary cation. The very last example I wanted to talk about was the unimolecular substitution, and this is one we'll get into more detail next time when we look at AN in a little more detail as well as DE. But the unimolecular substitution is, again, favored over SN2 under acidic conditions where we can really stabilize that DN step, that dissociation, and for quaternary electrophiles, so for very sterically hindered electrophiles, which actually have the advantage of hyperconjugative stabilization of that cationic intermediate. And what I mean by that is they can very easily stabilize cations through hyperconjugated donation. So whereas this would be a very crowded thing for a nucleophile to attack, say in its neutral form with the leaving group attached, once it's got that positive charge, it's fairly stable for a cation because of hyperconjugation. You should pay close attention to the stereochemistry here. Notice that it's kind of on a squiggly bond, and if that's tough to see, it's on a bond that looks like this to represent either up or down stereochemistry. The SN1 reaction is not stereospecific or, in many cases, stereoselective. This is in contrast to the SN2 reaction, which we saw did have a stereoselective requirement based on its molecular orbitals. The SN1 reaction doesn't have that requirement. We'll look at that in more detail next time. But you should think about why that would be the case. And to really understand it, it's a matter of the molecular orbitals of this cationic intermediate. For instance, you see one example here in that portion of the slide. And we'll look in more detail at AN and other reactions that involve AN next time. So just to review really quick a lot of what we talked about, under acidic conditions, compounds with leaving groups will dissociate to form cations and stable anions. We saw that the anions typically don't undergo chemistry. It's the cations that tend to be more reactive under these conditions. And they can undergo steps like DE, AN, 1,2-R, and others that we'll get to later on. We saw that the favorability of these reactions is governed by the stability of the charged species. So factors for cations like hyperconjugation, delocalization, hybridization, and like figure in there. And for anions, we see factors coming into play like delocalization, solvent effects, pKa, things like that. And so many of these factors that we've talked about already can be used to explain and can be applied to reactions that you may have never even seen before. And many times in organic chemistry courses, this is what makes organic chemistry so difficult. It's going to require you to apply general schemes to very specific reactions that you may never have seen before. And so having a general scheme in your hands and being very adept with it will help you, I think, no matter what organic chemistry course you're taking. So next time we'll take a closer look at the AN and DE steps and really sort of continue barreling our way through the elementary steps of organic chemistry. When we get done, hopefully you'll have a great appreciation for the various mechanistic possibilities in organic chemistry and for the fact that really, despite the massive variety of reactions that we see, they can really be reduced to a very small number of elementary steps. So thanks for watching, and I'll see you next time.